initially, right, I put a few bacteria inside, so there is a lot of nutrient per bacterium, right? They're not limited by the nutrient, right? So the R strategist goes faster than, right? So this is biomass. Okay, the R strategist goes faster than the K strategist. But as the biomass grows, as the total biomass grows, so we can do the total biomass like this. Okay, this is the total, right, A plus B. So as the total biomass grows, the nutrient level inside the chemostat drops. And we reach a situation where it drops so that species A, right, its C star now is above the nutrient concentration in the chemostat. So this species A will now have a negative term here and will fall exponentially, whereas the K strategist, which in our case has a lower C star, because KB is small, he's going to win. And he's going to win at a rather shallow slope, right, because there's not so much nutrient left, but he's definitely going to win, and actually I should make this, of course, asymptote to the total biomass. Right. So this is an example of Tillman's R-star theory. And again, you have the simulation code, so I encourage you to play with it a little bit and to check out the various cases, limits. Yes? Okay, so I've been asked to repeat. I'll do this briefly. The key is here. Okay, the key is here because both species get diluted at the same rate, 1 over big T. Okay, but they don't necessarily grow at the same rate, right? So what dictates their per capita growth? Two things: the nutrient concentration, C, and also their Kg max, right here. So the nutrient concentration doesn't stand alone. It depends on how well I can uptake the nutrient. The smaller K is, the more, the closer I can go to C equals 0 and still be able to maintain reasonable growth, right? So a large K means that I can only maintain reasonable growth at a large C. Okay, so we can define a C star, which is the point where this goes negative. Well, actually, when this is exactly 0, right? So if C star falls below that, then it goes negative. And now we have two species, each with its own C star A and C star B. So they will coexist if C star A exactly equals C star B. But this is extremely unlikely, right? These are biological systems, and to fine-tune even one parameter to fine-tune is highly unlikely, but to fine-tune two independent parameters is extremely unlikely, right? So typically you would have one of the C stars smaller than the other. And this is the species that is going to win. And it's going to win because the biomass, the total biomass of both species will keep growing, which means the nutrient density inside the chemostat will keep falling, right? The nutrient density inside the chemostat has, right, these negative terms, right, with both species, right? So as the biomass grows, this d to dt becomes more and more negative. And as a result, the nutrient inside the chemostat will drop so that it's lower than one of the species C star, but higher than the other species C star. And this means that the species that has the higher C star will get washed out, just like we did the washout scenario for a single species. Okay? Now you have two species, but only one will get washed out, and the other will survive. Yes?
So in this experiment, we're not giving nutrients to the system again. It's just like a constant volume of nutrient.
Oh, we're all the time supplying C in, but it gets consumed all the time as well,
yes,
right?
We're
So,
adding more nutrients.
no, we are. All the time we're supplying C in. This is the only positive contribution to the C to the T, right? It's a plus C in and then a minus, 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 right? So we're all the time supplying, we have a pump supplying fresh nutrient to the system all the time, okay? But then we also have a pump extracting whatever nutrient is in the system. And also, the nutrient gets consumed and converted to biomass, right? So this is exactly the conversion of the nutrient to the biomass of species 1. This is the conversion of the nutrient to the biomass of species 2. So as the biomass grows, the nutrient inside the chemostat drops, okay?
So the rate of the nutrient is the constant thing here?
Well, yeah, the rate of the supply and also the rate of the dilution. They are the same rate because we have the same volume flowing in and out of the system, because otherwise the volume of the system will change, right? So if we want to maintain a constant volume, then the same amount of volume per unit time that is put in is taken out. But we put in just nutrient at the level C in, and we take out the nutrient inside at level C, and also the species that are inside, right? So this is the washout scenario where we take out the species faster than they can reproduce, and then they wash out. And what this Tillman-R star theory shows is this situation where one species gets washed out and the other doesn't, okay? So it will dominate the system, and this is the equilibrium. So again, very simple math, but actually very deep insights. And right, I mean, I guess typically when you study sort of normal physics, you don't usually get to stuff that happened in the 1980s, right? At least not until your PhD. Usually, even through the master's degree, you're usually stuck in the 1930s or 40s at the very latest, right? So it's not because people were stupid, obviously, it's because it took time to develop these ideas and these concepts. Okay, so let's press forward, unless there is one quick question still. Yes? Yes, the R strategist is one that maximizes the maximal growth rate, the Kg max, and the K strategist is the one that minimizes the Monod half constant K, okay? So this often comes at the expense of the other, because how do I have a low Monod K? Well, I invest resources in taking up nutrient from the environment into my cell efficiently, okay? So if I do that, I can take up nutrient efficiently at lower levels, but these resources that I spent now mean that I have less resources to grow at a maximal growth rate, right? So typically, these things would come at the expense of each other in a very nonlinear fashion, right? Okay. So Tillman's R-star theory actually led us to something very deep and very confusing in ecology that hasn't been completely resolved, actually, all the way back to the 1930s. And this is the so-called competitive exclusion principle and the paradox of the plankton. Competitive exclusion principle and the paradox of the plankton. So we go back to 1932 to a chap by the name of Georgi Gausser, not to be confused with Carl Gauss. And he was a Soviet scientist studying the growth of bacteria. He's actually quite an interesting person because after he did this competitive exclusion principle, which we still teach today, he actually went to develop antimicrobial treatments, right? So these are very early days of antibiotics. And his treatments apparently saved hundreds of thousands of Soviet lives in World War II, right? When antibiotics was still not widely available and used. So definitely a lot of impact, this person. And specifically, the competitive exclusion principle, this was an experimental observation where he grew two competing species on the same limiting resource. Okay, so we discussed Liebig's law of the minimum yesterday, right? So there is one limiting resource and now two competing species. And guess what? Only one survives, right? So the other survives. Okay, the other one outcompetes the other. One goes extinct and the other takes over the entire population. Right? So now that we know Tillman's work, which is 50 years after, yeah, it makes perfect sense, right? But first, this was observed, okay? Okay, if you have several types of nutrient, right? If you have several of nutrient, right, let's say we have M nutrients, then you can have at most M coexisting species. Okay, why is that? Because each of these nutrients will now have its own C star, and each of these C stars will have its own C star specialist, the one who is best at living at the lowest C star, right? And he would bring down that nutrient down to the low C star and dominate the ecosystem. So this is a simple generalization of what we just did with Tillman's R star theory, right? Which says if you have multiple resources, then you can have the best one in each resource type. Okay, so you can have coexistence of multiple species, but this is a very hard constraint. Okay, because how many different resources can you have? Not so many. How many different species of microbes can coexist? An astonishing number, right? If you take a gram of soil or a milliliter of ocean water, you have easily 1,000 species or more coexisting, okay? It's unlikely that there are 1,000 different resource types in these situations. We'll get back to that in a second, but before that, I'd like to mention, right, this was rigorously proved by a landmark paper by Armstrong and McGee, 1982, which is called, sorry, 1980, which is called the competitive exclusion principle. Right? So this is an actual proper mathematical proof stating that if I have m resources, I can have at most m coexisting species, all based on this logic that we just learned. Okay, but now, so this is the competitive exclusion principle and its history, dating back from Gauss's observations up until the complete mathematical description. But this posed a huge problem. Okay, and this problem was called the paradox of the plankton by a very famous ecologist called Hutchinson. Hutchinson, 1961, the paradox. And the paradox of the plankton is basically stating what I just said in a gram of soil and a milliliter of ocean water, but even being more explicit, if you look at Arctic waters, okay, you can have a huge abundance of different plankton species, but actually these waters have very few nutrient types. Okay, so the reality meets and clashes completely with the math, right? The math says we can have at most a few species coexisting in the Arctic waters, okay? Also, simple lab experiments say the same thing, but the reality is different, right? So natural ecosystems are incredibly diverse, especially microbial ecosystems. And this is the paradox of the plankton, and this paradox has employed theorists basically since then up until today, right? So this is the gift that keeps giving. So what did people say about how did they resolve this paradox? Because of course nature doesn't have paradoxes, right? The paradox is only because we are not understanding the theory correctly, right? So some ideas that were floated around, all of them are very powerful, and all of them are probably correct within certain contexts. Right, so temporal variability. Right, the chemostat is a constant environment in time. But we discussed briefly yesterday how ecosystems, natural ecosystems often fluctuate with time, right? The obvious fluctuations, day, night, seasons, and so forth, but also stochastic fluctuations as well, right? So once we introduce temporal variability, then you could think of situations where for a given time, one species thrives, and then a bit later, it goes down and a different species thrives, but none of them actually reach the point of complete takeover or extinction, right? They kind of all get their day in the sun kind of thing, right? Another thing which was already asked yesterday, I think by you, is spatial heterogeneity. Right, so the chemostat is well mixed, but nature is not well mixed. And as a result, we can have lots of different microenvironments in different spaces, and each microenvironment has a different nutrient concentration and therefore a different dominating species. Okay, so then when we do an experiment and we sample a macro environment, right, then we average out all the different microenvironments and we say, oh, look, this is incredibly diverse paradox, you know. Actually, an interesting thing to consider here is your mouth, right? The microbiome in your mouth is very, very diverse, and it has a lot of structure. Right, so lots of different microenvironments in the mouth microbiome. Another thing that is completely neglected here is predation, right? Some species eat other species, or toxin production, right? Some species poison their competitors, and so forth, right? And finally, and I'd like to mention this briefly, is the notion of metabolic trade-offs. Okay, and I'm a little bit biased, I have to say, because this relates to work that I did in my postdoc and actually up until today. Right, so what do I mean by metabolic trade-offs? So very important work that relates to the paradox of the plankton and species coexistence in the chemostat is work by Pana Posfai, yeah, Thibaut Tefumier, and Ned Wingreen. Right, so this is a beautiful paper in PRL from about 8 years ago. And what they did was, they said, well, let's say we have now several substitutable resources. Substitutable resources. For example, I mentioned yesterday in tropical rainforest soils, the limiting nutrient is phosphorus, but you can have organic phosphorus, or you can have inorganic, right, or mineral, if you like. Okay, so this phosphorus, this element which is needed, can come either in mineral form or in organic molecules. Okay, so this is still a single limiting resource, but now there are two versions of it. So you can think about how you would have certain specialists that specialize only in consuming organic phosphorus, okay, and cannot consume the inorganic phosphorus at all. They don't have the right biochemistry. Or specialists that only consume this. Or generalists that can consume both. But the key is that you can't be good at everything, right? You can specialize in one, or you can generalize, but you have a fixed enzyme budget. Okay, so I have a fixed enzyme budget. I can put all my enzymes just to eat this. I can put all my enzymes just to eat that. Or I can split my enzymes. Some enzymes can do this, and some enzymes can do that. Now, this is feasible because it's very crowded inside the bacterial cell, right? Bacteria have been optimizing themselves for approximately 4 billion years. Okay, and they operate very close to their biophysical limits. Okay, so this is a zero-sum game. Okay, I can, of course, put more enzymes into metabolism at the expense of something else, okay, like maintenance of cell wall, growth, and so forth. I can do that, and this is sort of the contemporary work is about that. But let's assume for a second that I have a certain fixed amount of metabolic enzymes, and I can just choose which strategy to specialize or to generalize. Okay, so on the one hand, this is feasible. On the other hand, this is fine-tuned. Okay, this paper assumes an exact same metabolic enzyme budget, and that's not completely reasonable. Right? it's reasonable to say all species have about the same budget, but to say all species have exactly the same budget, that's a bit stretching it. But the fact that they used the same exact budget for all species allows us to overcome Armstrong and McGee's theorem, right? This is a mathematical theorem. It's always correct, but it assumes certain things. And it assumes that you don't fine-tune. Just the way that we did earlier this hour, the situation of C star A equals C star B, that's fine-tuning. Okay, so this is a different form of fine-tuning that I have a fixed budget. Okay, so yes, this doesn't completely resolve the paradox of the plankton because this assumption is a bit of a stretch. But given this assumption, they showed, and it's a beautiful paper. I highly recommend you to read it. Of course, I'm a bit biased, but okay, it's not my paper, so I'm not that biased. They show that under this condition, you can actually have as many species as you want coexisting on a few limiting resources. Okay, so one criticism about this is that this fine-tuning, of course, is stretching us a little bit too far. But then you can say, and that's reasonable, it becomes a question of timescales, right? Let's say that things are not completely exactly fine-tuned. They're just approximately the same enzyme budget, okay? So that means there will be some time for extinction, okay? Now, this time for extinction could be long enough that things in the environment will change, right? So you start to have a competition of timescales, how quickly the environment changes versus how quickly the less competitive species die out because this is violated. Okay, so this was enough about that. I think, yeah, just to take away, so this is the end of this chapter on the chemostat. And I would like to say that the take-home message for this entire chapter is how we started from a very simple system dating back to 1950 and observations from 1932. And we gradually developed the intuition of what is washout, what is competitive exclusion, what it means for species coexistence, and then actually reach the point that here we have various proposed mechanisms for species coexisting, including one which is quite new, which involves the trade-offs in the metabolic capacity.
Excuse me, I didn't understand how this assumption somehow resolves the paradox. Can you please repeat it briefly?
Okay, so I didn't really explain that, right? I was asked how the fixed enzyme budget resolves the paradox. For that, we would have to invest at least an hour in going over that paper. And even though I love that paper, and for me it's a very important subject, I think in the context of this school, it's not a main topic, right? So I didn't actually tell you the mechanism, how it works, but I tried to give you an intuition that this is the fine-tuning, similarly to how we had coexistence if C star A equals C star B, that's fine-tuning. This is a different form of fine-tuning, but essentially this notion of fine-tuning allows us to overcome Armstrong and McGee's theorem because fine-tuning can overcome this theorem, right? So this is a more intuitive explanation rather than exact math. Yeah.
So you said the paper by Taifumi explained that you can have as many competing individuals given a small amount of resources.
A small amount of different resource types, yeah.
Okay, they are talking about the amount of types, not
Types.
the quantity per resources.
Yeah, I'm not talking about the quantity of the resources, I'm talking about the resource types, right? So this whole thing is about how many different resource types. The idea is that for each resource type, you could have at least one species that could potentially survive. right, that doesn't get washed out completely. And then if you have two species on one resource type, only one would win, right? So if you have M resources, you could have M species at most, or less.
This is what the Armstrong said.
Yes, this is the competitive exclusion principle, yeah, as formalized in this work, Armstrong and McGee. But even before they formalized it, right, it was recognized a lot before that by Hutchinson that there is a paradox, right? Yeah.
Yeah, but in the paper, like they prove that we have a lot of species with not a lot of types.
Yes, yes, a lot of species, but not. You could have only two types of resource, and you could have thousands of species coexisting, right?
So this is what we have in reality.
Well, yeah, it goes, this is what we have in the reality. It goes a long way to explain. It's one of the mechanisms used to explain the apparent paradox. Yeah. But like I said, this paradox is the gift that keeps giving. People keep coming up with new ideas how to resolve this paradox, right? And like I said, these are all probably true, right? But the context depends on the precise details of the ecosystem in question. Okay, so now we move forward to Robert May. This is really exciting, actually. This is one of the, I think, most astonishing papers of the 20th century. So I'm curious, just could we have a quick hands up, who has ever met random matrix theory before? Oh, quite a lot of people, okay. Good, so this should be pretty easy for you. I'm not a random matrix theory person at all, so please excuse me for the rather naive explanations. But this is probably going to be enough, and anyway, my explanations don't assume that anyone knows random matrix theory. Okay, so we go back to Robert May. And he wrote a seminal paper in 1972. Again, this is one of the papers that is really worth reading. This is like a 2-page paper in Nature, right? With basically 2 equations, okay? But highly influential, right? So let me give you a little bit of background, right? Robert May asked, when is a complex system stable? This was the question, which we're going to answer. But let's go back a little bit in background and ask what happened before Robert May. And this paper really presents what is called a paradigm shift in science, right? There is this notion that everyone thinks one thing, and then comes a paradigm shift, and then suddenly everyone thinks something completely different. Okay, and this paper, I think, is a great example of such a paradigm shift. So what is the paradigm that was shifted? Right, so it was generally thought, right, before May, it was generally thought that the more complex the ecosystem, the more stable it is. Okay, now this is reasonable. Okay, again, people weren't stupid before May, not at all. Okay, so why did they think that? Well, first of all, if you observe nature, nature is very stable, right? We can abuse it terribly, and still it looks like it handles things. Okay, and also nature is incredibly complex, right? So this is a great starting point to say that complex ecosystems are stable. Also, another observation, which is consistent with the previous thought, was if now you abuse nature too much and you remove the complexity, okay, at a certain point the ecosystem collapses, becomes unstable. right? So, you can overfish, you can poison the waters, you can, and still every year you get enough fish but then you cross this threshold and suddenly the fish population collapses, and so forth, right? So this idea that a complex ecosystem is stable has very strong intuitive roots, right? But then people started questioning the math, and it's worth mentioning a paper by Gardner and Ashby. So it's fun, right? Because Robert May, in his 1972 paper, starts by saying, Gardner and Ashby showed that, that's where he starts, right? And what they showed that even simple systems can lose stability with increasing complexity. Right, so they took a very simple system. So they had computers back then already, but they weren't very good. So they could write computer simulations for very small systems. And they did that. They wrote a computer simulation for a small system and then made it more complex and showed how it becomes unstable. Okay, so Robert May, who was an incredibly influential theoretical ecologist and physicist by training, so he knew physics, and he thought, I could do better than their simulations. I can actually write something very robust mathematically using random matrix theory, right? So we asked, what is the probability that a large randomly assembled community is stable? Okay, and he has two quantities here. He has n, which is the number of species. He has three quantities here, actually. He has c, which is the connectance. So when we say connectance, we mean how many interactions there are between the species. We'll formalize this in matrix form in a minute, right? But basically, when c equals 1, then every species interacts with every other species. When c equals 0, no species interacts with no other species. And, c equals half means that only half the interactions are present, right? And also, he has sigma, which is the standard deviation of the interaction strength. Okay, because you can interact strongly or weakly with other species. And with just these three parameters, Robert May reached this paradigm-shifting conclusion. Okay, so what is the formalism? The formalism is very simple, but then it will rely on some highly non-trivial random matrix theory results, which we will not derive, we will just state. Okay, so the formalism is that we have a general dynamical system right, which includes x vector species, right? So this is a vector of n species, or n elements, if you like. This doesn't have to be ecology, right? So a dynamical system means that we can write down the time derivative of this vector as some function of the species abundances here, right? So let's assume that it has a fixed point, x star, right, such that, of course, f of x star is 0, right? That's what makes it a fixed point, right? So this is 0, and then d to dt is 0, and then we're at steady state. Right, so now you can look at delta x, which is x minus x star, and you can say that d of delta x to dt is the Jacobian of this system, right? So this is a matrix, of course, times delta x. And the Jacobian matrix is simply the derivative of f by x at x star. Okay, so this is a simple linearization of the complex nonlinear dynamics near the fixed point. Okay, we're basically, what is this? This is basically a Taylor expansion to first order about the fixed point, right? So a small perturbation about the fixed point. We put the system at its fixed point at x star, and now we slightly perturb it, and we say, well, the dynamics are dominated only by the first derivative at the fixed point, right? The first order Taylor expansion of the dynamics. Right, so now we have this Jacobian matrix, and this is where we're going to have a lot of fun with random matrix theory. So before I do that, any questions about this? Okay, so of course we want delta x to decay, right? We want delta x to decay because that means that we go back to steady state. The other option would be for delta x to explode, right? Because we have d delta x to dt equals something times delta x. So, this thing could be either positive or negative. If it's negative, then delta x decays to 0, which means we're back to steady state. If it's positive, it means that delta x explodes, right? Which means we leave this steady state and we go somewhere completely different. And we'll talk about that in the end of this part. Okay, now this is these are vectors, and this is a matrix. And of course, what we're actually interested in are the eigenvalues of this matrix. And in fact, what we need is for all the real parts of these eigenvalues to be negative, right? So the eigenvalues in general could have a real and imaginary part. The imaginary part is not going to explode anything, right? It's just going to make it go around in circles, right? But the real part, if it's negative, if all the real eigenvalues are negative, then delta x will decay to 0 and we're back to steady state. But even if we have one positive real eigenvalue, then we lose stability, right? So this is clear. So basically, May's criterion is, when can I be sure that all the real parts of these eigenvalues are negative? Okay, so let's be a little bit more specific. So now we have a random matrix. And this is asking for a lot, right? Saying that the Jacobian is a random matrix, right, means that basically the species-species interactions, which are the off-diagonal elements in the Jacobian, are completely random. And this, of course, is not correct generally, right? I mean, an ecosystem is not just a bunch of randomly interacting species, right? So we'll come back to that at the end of this chapter. But for now, let's bear with Robert May, okay? He also put -1 on the diagonal. Okay, so this -1 is, if you like, self-regulation. Regulation. What does it mean, self-regulation? It means that, in general, the species, each species, this is diagonal, goes back to its steady state value because of limiting factors. It could compete for space, it could compete for nutrient, right? It's self-limiting. There is a steady state value that it would tend towards, okay, if there weren't interactions that would affect it, okay? So we put a -1 here, and actually you can generalize, right? You can actually draw this diagonal from a distribution as well, with a mean of -1. Okay, so this is the setup. And the only sort of unbelievable thing here is that we drew these interaction terms randomly, right? And again, I'll talk about it more at the end of this chapter. But since it's actually incredibly difficult to measure these interaction terms, then putting random numbers is not that silly, right? Because what else can you put inside? It's incredibly difficult to look at an ecosystem and to say, oh, you know, species A interacts with species B with this value. You know, of course, it's possible. You would have to have very good time series experiments and very strong machine learning, right? Very clean data. So this is much more reasonable in lab experiments where you can run the same experiment many times and so forth. But even then, this is very, very hard. Okay. So we said that Robert May was trained as a physicist, and he knew nuclear physics. And in fact, he knew something which we call Wigner's semicircle law. Right, so this is a fun statement. So Wigner was a quantum physicist. Eugene Wigner was a quantum physicist, and way back in the 1950s, when they tried to work out the spectra of these heavy atoms, you know, like for example uranium. Okay, so there's lots of protons and lots of neutrons, and they really had no way of working out the elements of the Hamiltonian. Okay, so he said, well, let's pretend that the Hamiltonian has random matrix elements, right? So it's a random Hamiltonian. That's fun. Okay, and then what is the eigenvalue spectrum of this random Hamiltonian? And turns out that the distribution of eigenvalues, right, so rho here is the density of eigenvalues, follows semicircle law. Okay, let me plot this. So again, there is a simulation of this. Of course, it's very easy to simulate. You just make a bunch of random Hamiltonians, and you diagonalize them, and then you make a histogram of the eigenvalues. And lo and behold, right, so this is the histogram. And they obey this semicircular law, right? So you have the most eigenvalues about 0, and then the amount of eigenvalues decays, right? So this is lambda, the eigenvalue, and this is the frequency in the sense of how many times that eigenvalue appears, right? And it obeys the semicircular law. I had a question, but in a second I'll just finish this. And the support of this is between minus 2 sigma to plus 2 sigma. Right, so this is an asymptotic limit for a matrix that is infinitely large, okay? Right, so n goes to infinity. Of course, in finite n, you could have sort of rogue eigenvalues. But in general, so it's a finite size effect, right? But asymptotically, you will have all eigenvalues lie within this space. This is Hamiltonian, so it's Hermitian, right? So it has a very specific symmetry. And therefore, all the eigenvalues are real. And basically, half of them would be positive and half of them would be negative. Questions? Yeah?
So remember the list bit, but the distribution of the entries is Gaussian, or you just take the variance?
So, yeah, excellent question. I think that originally with Wigner, it was Gaussian, but we're going to extend it a little bit. And like I said, I'm not a random matrix expert. And in fact, the extensions, so I'm just going to extend it now, but the extensions actually date after May's theory, right? So this was generalized more and more and more, right? But let's generalize it.
You said the Hamiltonian has a symmetry,
It has to be Hermitian, right? Otherwise, it's not Hamiltonian.
not the interaction matrix in our case.
Exactly, it's not. So we have to extend. So it's not enough to know Wigner's result. We need to go beyond Wigner, right? So let me just restate this question. The Hamiltonian has a symmetry, right? Aij equals Aj complex conjugate, right? But the ecosystem, we said, is completely random, right? So there is no obvious symmetry between Aij and Aji, and also ecologically speaking, it doesn't make sense. Like, for example, if one species eats the second, right, then you would have antisymmetry in the Hamiltonian, right? In J, right? Because you would have a positive interaction for the species that eats, for the predator that eats the prey, and a negative interaction for the prey that gets eaten by the predator, right? So even, it doesn't make any sense for this matrix to be symmetric when describing a real ecosystem, which is why we have to go beyond Wigner's semicircular law and go back and go forward in time a little bit to the so-called Ginebra and Girko's circular law. Circular law. So there is quite a lot of time between Ginebra, which is 1965, so this is before May, and Girko, which is 1984, a lot after May. And there's probably still people working on generalizing the disk law. Okay, so what am I talking about? Let's now have a random matrix. And Ginebra, I think, still used Gaussian entries, but didn't require symmetry, right? By the time we reach Girko, which is after May, these could actually be complex numbers. They don't have to be real. And also, they don't have to be symmetric. And in fact, this is a rather loose set of criteria for the Ginebra disk to work. But since we're talking about May 1972, he's still here, right? But as like I said, I'm not a random matrix expert at all, so I cannot tell you what is the state of the art in random matrix theory now regarding when does this apply and when it doesn't. But for our case, it certainly applies. Okay, so the law is that if I take now a random matrix with n elements, right, and we normalize it by root n, then all eigenvalues, now the eigenvalues in general are not real, they're complex, and they will form a disk, right, will fall inside a circle of radius sigma. Okay, so it looks like this, and again, it's very easy to write the simulation, and you have the code, and you have the pictures here in the lecture notes, right? But you take an ensemble of random matrices, and basically you normalize them by 1 over root n, and you plot the eigenvalues, and so this is the real part, and this is the imaginary part, and all the eigenvalues will fall inside this disk of radius sigma. Okay, this is quite an astonishing result. I mean, even Wigner's result is very astonishing, right? But this is magic. Yeah. Again, this is an asymptotic limit, so actually even in the simulations here in the lecture notes, you will see occasionally a dot that extends away from the disk. It's because this is asymptotically correct for n goes to infinity, but for a finite n, of course, you can have a conspiracy of values that actually takes you away from this just by a little bit. Okay, so these results are fairly universal. And again, I'm not sure exactly what are the mathematical criteria up to date into when they apply and when they not. In May's context, okay, and now it means that if we have, so going back to May, we said that we had 3 parameters, the system size, the number of species, right, n. So we had n, the number of species. We had c, the connectance, and we had sigma, which is the interaction strength. Right, so in this context, we would have that the real part of the eigenvalues, which is what we're interested in, would lie between minus sigma root nc to plus sigma root nc. Okay, this is still a random matrix, and we haven't taken into account the -1 on the diagonal. So let's do 2 things. One, let's briefly prove why this is correct. Okay, and given this, okay, and second, let's briefly remind ourselves of linear algebra and how the -1 in the diagonal affects this. Okay, so let's briefly prove this result. Right, this is not it's clear that the root n here and the sigma here conspire to give a root n here if we don't normalize by root n. Okay, I think that's pretty clear. But it's not utterly clear why the connectance c is inside the square root. Right, but it's very easy to show. Right, we have our random matrix which has elements, right? We take a single row which has elements x1, x2, x3, so forth until xn, right? And it's composed of 2 parts, right? It's composed of, so each xi is a product of eta I, and eta I is a Bernoulli variable, random variable, which is equal 1 with probability, well, Bernoulli, and equal 1 with probability C, right? This is the connectance. Basically, the element exists with probability C or is 0 with probability 1 minus C, yeah? And yi, which are just the Gaussian random variable with standard deviation sigma. Right, so now each element in a row of this matrix is the product of if it's there or not, right, which is a Bernoulli trial. It's either 1 or 0. Eta I is either 1 or 0. It's 1 with probability C, and it's 0 with probability 1 minus C. And also the value of the Gaussian of width sigma, which is centered about 0. Okay, so now we can write the variance of this single element in a row, right? The variance of xi is the expectation of xi squared because the mean is 0, right? Because the values yi have a mean of 0, so we just have to look at the expectation of x squared, which is the expectation value of eta squared times the expectation value of y squared. Okay, but of course, since eta I is either 0 or 1 with probability 1 minus c and 1 with probability c, okay, then of course eta I squared equals eta I, because 1 squared is 1 and 0 squared is 0. Okay, so what we have, that this is the expectation of eta I times the expectation of yi, and the expectation of eta I is exactly c, and the expectation of yi is sigma squared. Okay, and now if we look at the entire row, which is the sum of all xi's, and we look at the variance of the entire row, then since these are independent variables, the variance of their sum is the sum of their variances, right? So it's the sum of the variances of xi, and therefore we get the nc sigma squared, right? So if the variance of S is nc sigma squared, then the standard deviation would be sigma nc. Okay, so this is how we introduced the connectance C into this Genebre-Guercot disk. And we have just one missing element in order to complete Robert May's statement, and that is a brief reminder of linear algebra. And the statement is that if I look at the eigenvalues of a matrix M minus I, right? So M is a random matrix, and I is the identity matrix. So M minus I gives me the -1 on the diagonal, the self-limiting that we talked about, the tendency of each species to tend towards a steady state value, right, because of competition for space, nutrient, and so forth. Okay, so if V is an eigenvector of M, right? So MV equals lambda V, right? Then M minus I times V would equal lambda minus 1 times V, right? Which means that lambda minus 1 is an eigenvector of M minus I. Okay, so briefly stated, this is just a reminder, this shouldn't be a big surprise to any of you, hopefully, that by putting -1 on the diagonal here, we have shifted the Genebre-Girko disk so that instead of being centered at 0, it's now centered at -1. So let's do it like this. Right. It's now centered at -1. We just shifted the real parts of the eigenvalues by -1. Okay? So now we've done everything we need in order to reach Robert May's seminal result. And what is the seminal result? We want that no real part of this matrix, no real part of the Jacobian is greater than 0, right? Because if I have a single eigenvalue, which is the real part is greater than 0, it means that d delta x to dt would have a plus something times delta x, and this will explode, right? So we need all of these eigenvalues to be negative or 0. Okay, so since we already derived the result for sigma root NC, okay, what we actually need is for sigma root NC to be less than 1, right? This 1 is not a magic number. This 1 is because we shifted by -1. Okay, if we had shifted by -2, then it would be less than 2, right? But we could always scale things so that 1 is the interesting quantity. Okay, and this is Robert May's criterion for stability. Okay, and this is the paradigm shift. Okay, we started off by saying that before Robert May, the intuition was that the more complex the system was, the more stable it is. And we have reached the opposite conclusion. Okay? If I increase the number of species, then I can cross the threshold and destabilize. If I increase the connectance between the species, so I form more connections between species, then I can exceed 1, okay, and fall out of stability. If I increase the strength of interaction between the species, I can exceed 1, right? For the system to be stable, these three things have to conspire together to be less than 1. It's such a beautiful, it's amazing, it's a 2-page Nature paper, right? It basically has this equation and the Jacobian equation that I wrote, well, I just erased it, but you know what I'm talking about, hopefully. Right, so much insight. This is Robert May's stability criterion. Questions before I expand a little bit on this and philosophize a little bit on this? Oh, maybe just before the questions. So you can also run the simulation on a bunch of matrices, which is what I did. And you have the figure here, and you have the code, right? So you can plot the number of species, and you can plot the probability for a greater than 0 eigenvalue, and the eigenvalue. And within what I put, the parameters that I put in the simulation, we see things rise rather quickly. This is May's criterion for C equals 1. And also, I did another simulation for c equals half. Right, so this is c equals half. You could play around with the numbers a little bit. What you can see is that this is fairly sharp, but not completely sharp. And again, this lack of complete sharpness is because this is asymptotically correct in the large n limit, right? So you can play around with sigma so that you shift everything to higher n, and then this will become sharper and sharper. But of course, the computational time will explode because you have to diagonalize a bunch of huge matrices, right, in order to derive this result, right? But very quickly, even in the small numbers, so the numbers here are actually 25 and 50, right? So these are not huge matrices, right? If we think about an ecosystem with 1,000 species, right, so this is much smaller than that. But even when I have only about 25 or 50 species, still this is pretty sharp, right? And very quickly, once you cross Robert May's threshold, then the probability of getting a positive eigenvalue becomes essentially 1, which means the system will inevitably destabilize. Okay, so this is very, very powerful, right? And I'd like to philosophize a little bit about this, but before that, questions? Yeah.
Assume that the minimum variable yi is 0, why this is a valid assumption for ecological processes?
That's a great question. So it's a good starting point. There is no obvious direction where you could say most interactions are positive or negative, right? So it makes sense that the average will be 0. But yeah, you're right. I mean, generally speaking, you should consider situations where the mean is not 0, the values are not drawn from Gaussian distribution and so forth. And like I said, you know, this field of random matrix theory is still continuing. I mean, as far as I know, some people are quite critical of Gierko's proofs and try to reprove some of his stuff more rigorously. And so forth. So this is a field that is still in evolution. I don't think we know completely what are the criterion for this disk results yet. Okay, and I'm really not an expert in that. Any more questions? Yes.
What if the connectome is 0?
Well, then nobody interacts with nobody, and you only have the diagonal, which is -1, so you will always go back to steady state, right? So this is the trivial case where... Yes, this is coexistence, and it's stable coexistence in that all species just always go back to their steady state, right? Yeah.
Yeah, the chemostats, the equations of the chemostats at the beginning, they have a connectome greater than 0.
Okay, so this is an excellent question. How does this connect to the chemostat before? So the answer is it doesn't immediately connect, and I'll tell you why. When we modeled the chemostat, we modeled things according to so-called consumer resource models, right? So what we had was a bunch of consumers, and they interacted with each other only through the nutrient, right? So one affected the other because it stole some nutrient to itself, and then the other species had less nutrient, right? So you can think of this as a mean field of nutrients, and every species interacts only with the mean field, but not directly with the other species. So this is one type of modeling, consumer resource modeling. This is a completely different type of modeling, which is actually related to our next chapter, generalized Lotka-Volterra equations, where you only consider the direct species-species interactions. There are no nutrients here, at least not explicitly, right? And you only consider how species interact directly with each other in a pairwise fashion. Okay, so these are two completely separate modeling paradigms. Now, it is possible to derive one from the other in certain conditions, but it's not easy and it's limited, right? So these are the two, and this is why this would lead us naturally to the generalized Lotka-Volterra equations. So here you don't meet the paradox of the plankton, because you don't have this issue of competing for a limiting resource and so forth. So it's a nice way to solve the paradox of the plankton. Just pretend that resources don't exist and only species interact with each other, right? Yeah, but that's a really good point. Yeah. Okay, so I was going to philosophize about that, but we'll probably do that starting the lesson tomorrow. Briefly speaking, you could have either a positive interaction or a negative interaction or a zero, right? But I will make a table of what ecologists call mutualism, predation, commensalism, and so forth, right? Yeah.
In the circular law, the matrices have a diagonal which is also random, right?
Diagonal. Yeah. So like I said, you don't actually have to put -1. You can put a distribution about -1 and it would still work. So in my simulation, I actually put a distribution about -1, right? And you can see this here. We spoke about a single row, right? But what you care about is the mean over all rows, right? So that's what's important. Yeah.
Are there results that reduce the matrix, like when there are values very small, very close to zero, they become automatically zero, like a sparse matrix instead of a full matrix? Because maybe at the first approximation, we can say if the correlation between the two populations is 0.001, we can say that the first approximation is zero.
Okay, so this is a great question. The question is, can I take something which is close to zero to be zero? Well, generally speaking, from this formalism, no, but it does enter here in the sigma, right? Because the sigma tells me essentially how many close to zero elements I have, right? The larger the sigma is, the more I have elements that are far from zero, so the less I have elements that are close to zero. So, even in this simple formulation, sigma encodes a little bit what you said, but then there is a very big difference between 0 and 0.000 something here. But also, if you think about it, here, time doesn't matter, right? So it can take 100 years or it can take a second, right? If my eigenvalue is positive, then I will explode and I won't be stable, right? So my d to dt will be positive and I don't care if it's just a little bit positive or a lot positive, right?
But I mean, how would the eigenvalue distribution change? Maybe if we say, okay, this is a sparse matrix, let's say half of the, instead of messing with the connectors, we just say, okay, the values that are close to zero are zero. How would that affect
So I'm not sure exactly how to answer you, but why not mess with the connectors? What you just said was I'm messing with the connectors. I'm setting things to be actually zero.
Yeah, but
right.
If I mess with the connectors, I am still keeping the distribution the same. Instead, I say maybe I want just the outliers. So if the trees don't interact a lot with fishes, I say, okay, maybe it's 0.001. I say, okay, it's just zero.
So I wish I knew how to answer you better, but I don't. Okay, so our time has run out, so we'll continue with this tomorrow because there are a few things worth mentioning. We finished with the math part, but I really want to leave you with this astonishing result about complexity and stability, and I wanted to leave you thinking a little bit about human systems, right, and consider how the invention of social networks seem to have destabilized what appeared to be before pretty stable political systems, right? Turns out that when people start talking to everyone else all the time, then political systems can be destabilized quite easily. Think about COVID-19 and how in this ultra-connected world, this epidemic within weeks devastated the entire planet, right? And think about global supply chains that, an earthquake or a fire in one side of the world suddenly creates shortages in something seemingly unrelated in the other side of the planet, okay? These are all features of human systems that have become ultra-connected, and also, at the same time, less stable, right? So think about that, and we'll talk a little bit more about this tomorrow, and this leads very naturally to generalized Lotka-Voltaire equations. Okay, thank you.